All right, now let's resume with 4-bar linkages. And I'm sure you all, in your design notebooks or you're taking notes about some of these topics, have worked out the problem from before. We left you with, could we have like a picture frame and then a structure in the middle with some sort of linkage arrangement that allows this thing to move? So for example, unexpected results. A frame around here, we're in the middle of the frame, then this table would then be able to free float move nicely. We're going to need this later. That actually happened for a reason. How are you going to analyze that design? Does this make sense? Do I have a hope of this brilliant creation of adding all these links, giving me the motions I want here? Why should I bother to try to optimize these link lengths if this thing won't give me the motion I want? See, that's the purpose of why you have, for example, Grubler's equation to let you determine, do you have the degrees of freedom you want? And if you do, sure, go ahead and invest another n hours to figure out what's the optimal length of the links. Let's try it. Let's just count everything up. Here's our ground link, 1. And then I've got 1, 2 times 4. So then I've got 8 of these binary links, which are just 8 times 1 they count, links, 1 ground. And how about this guy in the middle? He's a quaternary link because he's got these 4 points. He still just counts as 1. So what's the total number I've got? I've got 8 plus 1 plus 1 is 10. So I've got 3 times 10 minus 1 minus 2 times, now how many joints? 1, 2, 3. These are simple pivots. They each count as 1, and there's 4 of them. 4 sets of 3 minus 2 times 12. This equals the degrees of freedom of this center stage. I have 3 times 9 minus 2 times 12. That's 27 minus 24. So F equals 3. I have 3 degrees of freedom of this platform. Is that right? Yeah, it is. This platform now can move around and rotate while being supported by these links. That would be an option, an alternative to, remember earlier I was sketching out some kind of an arm system like this with a table on the end. So this structure or this structure, what would you rather buy? What would you rather build? So you see, there are 2 concepts to produce a table according to the strategy of give me a table that is just using pivots. Remember, our other direction would be linear motion or prismatic joints. This is the revolute joint option. And later on we'll see how would you make a decision as to which one you want to build. A lot more complications here, a lot more stuff going on, but it's all based off of 8 of the exact same part. So when you start thinking about manufacturing, this really only has, quote, 3 parts: the center table, the outer ring, and then a whole bunch of these links. So a lot of commonality. Okay? And what would be up here? How does this relate to 4-bar linkages? Remember, we originally drew this as a 4-bar linkage. We didn't get the motions we want, so then we added more links. Okay? Now, let's now dive into the details of 4-bar linkages, which are one of the most extensively studied and used types of linkages out there. This is our simple 4-bar linkage. Here is what is often mathematically generically represented. This gray structure here, the coupler link, it can be of any shape and can have points of stuff attached to it, but fundamentally it's still just a binary link connected at its end. Okay? This purple dude, you may want to remember from the other day, we used as an example in reciprocity, where we used the parasitic motions of one linkage set to cancel out the other. So this is composed of nested 4-bar linkages, such that when these points here are bolted to ground, and I apply a force here, these links allow it to move this way. They want to shorten, but this linkage inner set wants to move that way and shorten in the opposite direction. The parasitic motions cancel, and as a result, as this stage moves perfectly in this motion without any parasitic motions. Whereas if I just had half the mechanism, as the stage moves, it gets that cosine error. Okay, that's very important. So a big part of linkages, you realize, is you got to look for, when you move in one direction, you get this little parasitic unwanted motion in another direction. Very, very critical in analysis. What's this thing here do down here? This is the same kind of linear motion stage, 4-bar stage, and it's got some very specific things called tuning blocks. We're pushing. Why are we pushing down here in the middle? Why aren't we pushing on the top of the stage? Okay, that's a very interesting advanced concept that you can read ahead if you want. But that's a very good tongue twisting. Why are you pushing in the middle and not where you want to be pushing for the action? What? Oh, I remember. Center of stiffness. Ah, where's the center of stiffness of this? And remember that thing we did about the slope coming down, the beam bending and the slope on the end, and you come back to a point where you just get pure rotation and not translation. There's some interesting hints there for you to scribble in your notebook and discover. This kind of, oh, that's interesting. Oh, that's weird. Oh, that's not behaving as it's supposed to. This is the essence of innovation and design and discovery, by the way. As you're going along from the ride of learning, don't just, yes, just take in what you're given. Oh, that was good. Chew on the information. Taste the flavors, all the subtle hints and essences of and track them down. Okay? Very, very important. You'll find, and when you're studying things, you'll often get ideas for things you never thought you had that'll be, boom, you can do your own innovation. Okay? Now, let's look at a very specific type of 4-bar linkages for booms. And you'll see booms happen a lot in cranes, lifting mechanisms, tractor linkages. You often encounter them where a load is out here and you want to pick things up. Okay? And if you notice what happened is, when I pick this up, load up, see the blue bar, how it remains parallel? That is why a linkage, as opposed to just an ordinary crane arm, when it goes up, you see the slope changes, can be very useful for when you're designing something, for example, like a forklift type structure to pick something up. So it will automatically, with 1 degree of freedom, keep things horizontal, right? So if my forearm was a 4-bar linkage, the load on the end would always be held horizontal. How would you actually design the details of that linkage? How would you do that? Okay. You do that through something that's called kinematic synthesis. Kinematic synthesis, it allows you to say, here's the motion I want to accomplish, and now fit the links to it. Okay? A very, very important type of kinematic synthesis you can do graphically is called the 3-point circle construction, or the precision point method. Right? And how do I make this loader here with these links give me the motion I want? Okay? How do I do that? What do all these lines here mean? Remember, there's the text that goes with the pictures here. Okay? So let's do an example. I want to use the 3 precision point method to find where's the ground pivot point for the crank and follower links for this sketch I have for some sort of scooper that I'm going to scoop up some stuff and in one linkage motion go and then dump it in the back. And where have you seen this kind of motion before? A trash truck. Trash truck comes along, little forks engage the dumpster, and as it picks up, then poof. That actually has an extra degree of freedom they can control. So when they pick it up and go level, and then just the last moment, poof. But you could do it in one motion. Okay? So what we want to do is we want to envision, you see here I start with this black link set at this point, and I want to bring it up here and swivel, and then dump. And what do I want my links to look like? Well, if you think about it, let's just pick one point here. And I want this point to go here, here, here. And this is my follower link. Excuse me, this is my coupler link. So you start with the coupler, and you draw 3 positions that you want your coupler to be in. Here, here, and here. Okay, so this is the first position, second position, third position. This joint of the coupler here is going to go here, here, and then over to here. You know that you can connect a line from here to here, and there's going to be some link on the crank that has to touch from a ground point to here, and the ground point's not moving, and then it's got to go in the next position to here, and then it's got to connect in the third position. So we need to find where this ground point is. How do we know where to find it? So this point on the coupler goes to here, and this point goes to here. Now we've got to find a ground point that is equidistant from each of these 3 points. This is the 3-point method. 1, 2, 3. So remember from our geometry class, and if you haven't remembered that, that's okay. If you take a line here, and then I'm going to take a second line here. So this point 1, we'll call that 1. This is point 2, 2. This is point 3, 3. I've just rotated around so it's a little easier to draw. I need to find a point somewhere around here that's the same distance from each of these 3 points, because that point will be the pivot point to which my crank link is attached. So, wow, how do I do that? Hold on. Calm down. Let's break it down. If I find the point that is the same distance from here and here, it'll be true that it'll also be the same distance from here, here, and here. What points are, how do I find the points that are equidistant from these two? Well, the middle of the line is where this is L over 2 and L over 2. How about this one? Nope, longer. But if I go straight up, this is called the perpendicular bisector. Every point on this line is equidistant or equal to these other 2 points. I can repeat that same logic over here in the perpendicular bisector like that. Every point in this perpendicular bisector is equal distance to the endpoints. And lo and behold, where the 2 perpendicular bisectors meet, that point is equidistant from all 3 points. So that becomes the pivot point for your crank link. Okay, that's what we did here. That's this point. This point, you can see here, I've got my perpendicular bisectors, boom, is there. You now do the same exercise for the other pivot at the other end of the coupler. It goes from here to here, here to here, and the red lines here show its perpendicular bisectors, and boom, that's the point. So you can say, great, no problem. I will now just connect up my crank link. But watch, as I move my crank link through the motions here, this one is going to bump into that point. It's perfectly legal to put a rigid link doesn't have to be straight. It can have this cutout shape in it. So as it moves, it goes around another pivot, for example. Okay, that's perfectly legal. All right? So this very, very powerful graphical method for, you just pick 3 positions and you're all set. You can very exactly figure out your linkage shape for a 4-bar linkage. Very, very powerful graphical tool. And you know what? For all you CAD folks out there who just can't get away from your CAD systems, this works great, because I could go into SolidWorks, Inventor, Creo, any of the programs I like to use, and in the sketch part, I can do these kinds of sketches and just graphically construct in sketching where I want my links to be. Very, very powerful. And then you can animate it too, very, very nicely. Okay? Now, we get to the really fun part, which is analysis. How do you figure out what kind of torques you need? How am I going to go in, and what is all this mess in here? How do I figure out what's happening? Let me just take my generic 4-bar linkage I kind of created here. And what kind of questions do I want to ask? Okay, I'm going to make this my crank. And I'm going to say on the crank, you know, it's got a motor that puts a torque in. And on my coupler link up here, at this point here, I'm going to be applying some kind of a force to it, always in the horizontal direction. How do I figure out when I apply a torque here, what happens up here? How do I figure that out? What can I do? Well, remember conservation of energy. And now you just start systematically, deep breath, taking your problem apart, labeling what you know. I know this length, I call it L1. And I actually often like to use not L1, L2, because I can get confused and mix things up. Let me start with a little cleaner drawing here. Okay, and I'm going to say that my ground length is A. Then my crank length here is B. And then I'm going to label C as being the length here along the coupler. And then D on my follower. And I'm going to label this angle from ground phi. Okay? And these will be my knowns. I'm going to use this purple for my knowns. A, B, C, D. I'm giving that, or I'm assuming that. I can change them later. And the input angle phi. And now what I need to solve for is if I have some position point up here, right? You can see my drawing here. I need to figure out what is the x and y positions of this point as a function of these variables. Oh, and we call this one here h. How do you do that? Now it's just a simple geometry problem. Okay? And what I like to do is create triangles. Okay? I can calculate I can know the position of this point B up here, right? I can make another position points, other triangles between here and down to here. I can start drawing all kinds of triangles. Which triangles do I need? How am I going to figure out what is where? There's something interesting here. What is going on with these red lines here? Why did I extend them down? What is happening with that? I'm going to get to that here in a minute. It's a very interesting problem. Meanwhile, back in your design notebooks, you guys should be thinking, wow, what a cool geometry problem. So if I know the torque coming in and a little bit of angle of motion, and I know then can figure out what's my little bit of x motion up here, then I know if I'm resisting that with a force, conservation of energy, that force times this little bit of x motion has got to equal this torque times that angle. Right? Now, you look at all this, you say, oh, well, I can't follow it. What's going on? What I want you to do is do the analysis yourself, starting from here. Come up with your equations. They're all closed form, very simple sequence of trigonometric relations. Write a spreadsheet, MATLAB, whatever you like to do calculations, and see if you can write your own 4-bar linkage analysis code. You could say, I can go to Google and get one by myself, no problem. Why do I have to write this? 2 reasons. When you write your own little bit of code for this, it allows you to go in and do things. Remember we talked about sensitivity analysis before. I can go in and say, I don't have B, I actually have B plus a little bit of manufacturing error. How does that little bit of manufacturing error affect how well I know what this point is doing? When you write your own code like that, it allows you to tweak, to push on your system and see what's right or wrong with it. Discover the sensitivities involved. How accurate do these joints have to be made? That's what it lets you do. Okay? So we'll come back to that after you guys have had a chance to think about it and go through that analysis. Remember, conservation of energy, drawing triangles so you can solve the triangles for what these positions are. Very important. Now, the coupler. The coupler is a really interesting thing. The coupler, if you pick a point on the coupler, and as it moves, you can track what it's doing. And the coupler curve can then tell you, are you getting beyond just a simple 3-point synthesis method, what is happening as this thing moves? And you may want to have your linkage accomplish some function like simulating running, or come and apply an adhesive and come back, and the next part comes in and it'll come back and apply the adhesive again. And it has to touch down at a certain angle. When you write your bit of code, your spreadsheet even, you can graph points, how they move as your crank moves. And that can then tell you, for example, this is the one particular linkage. It was a really, really sweet linkage. I really loved that linkage because the coupler, I could make it an interesting shape happen. Okay? So look at these different shapes. Why are these 4-bar linkages all these different shapes? It's to enable the coupler to do special things. Now, let's get back to our earlier discussion where I asked you, what were those red lines for? And now let's think about something. When the coupler moves, it seems to move as if it's its own little rotation. Well, that's what's referred to as the instant center. So in particular, if I make a linkage that looks like this, and let me make this a little easier to trace. You see, for very small motions, the blue coupler looks like it's just rocking. Can everybody see that? It looks like the blue linkage is, for very small motions, is just rotating. It's not actually translating, it's just rotating. Well, what that is it, in that instant in time, it is not really moving, it's just rotating about the instant center. And the instant center for any body, I draw a line along one of the guide links, and along another one. And where they meet is the center of action that these two guys have to work with. That is the instant center for this linkage. And that point here is, if I pick a point right between the two, that is how that coupler is rotating. about the instant center. It's a very, very powerful graphical tool that you can do when you're looking at a linkage to find out, for that moment in time, what is the coupler doing? You can think about a wheel rolling along on a surface. Where is the pivot point? Where is the instant center? What is actually happening as a wheel is rolling, right? So think about this here. Remember, the instant center of velocity for two bodies in plane motion is a point common to the two bodies which has the same instantaneous velocity in the two bodies. That's why we drew those lines together. Okay? It doesn't necessarily exist on the body, it can be off the body. The instant center is then used to determine the relative velocities between the different links, because remember, for that moment in time, everybody's rotating about that instant center. If you have the relative velocity between the links and the torque input to one link, you can use the conservation of energy, or parentheses power, to determine the output torque. Very powerful, powerful, powerful idea. So think about that earlier slide we had. See what we did here? These red lines, this was the instant center. When I find this instant center and I connect it to this point on the coupler, for that instant in time, this point on the coupler is moving, is rotating about this arc. So when I'm wiggling this crank over this length here, it's moving a little bit. Very, very powerful law. Okay? Fantastic for synthesis and analysis of linkages. Here we show a 4-bar linkage that's of particularly high interest. This is sometimes called a knuckle linkage, or you go over center. You want instability to happen. Watch here, I've got my ground link 1, 2, here's my coupler 3, my crank 4, my pivots. Let's say, and in here I've got a walnut. Let's make a nutcracker out of this, right? Think about, I want to open up a hazelnut or a walnut or something, and they can be really tough nut to crack. I want to put in a little bit of force so I can crack the nut. You've all seen nutcrackers where people basically take pliers and clunk, but you still have to sometimes squeeze really hard. Could I do something where I have a simple mechanism where I just push a little bit? I have this huge mechanical advantage. Can I get more mechanical advantage than I would by a simple lever? What happens when these two links start to straighten out? Where is the instant center, and what are the implications on the forces here? Right? What happens? What happens when the instant center comes down? Is there a point where I can predict an instability, and when I have an instability, I have huge forces? And the cool thing is, you can be doing this analysis just by drawing. You can draw things in different positions. Look where the instant center moves as the linkage moves. See what you can discover. So you can be doodling on the subway, on the school bus, anywhere you want, and learn so much just by graphically looking at things. And the math goes along with the graphical language too. So that makes it even cooler when it gets time to actually write your spreadsheet or your code to figure out and calculate exactly what's happening. So remember, with 4-bar linkages, always be projecting along the crank and the follower to find the instant center to see what's that instantaneous rotation of the coupler, what's happening. Okay? And what happens when you get to a point where the instant center crosses part of the linkage itself? What kind of instabilities do you get? Okay? Very, very powerful. So for example, here, let's find the magnitude and direction of the coupler point motion for this 4-bar linkage. We draw, these dashed lines go through the crank and the follower. This is our instant center point. The velocity of the coupler point is perpendicular to an imaginary line from the instant center to the point of interest. So I can go from here up to my point of interest, and this red vector, that's the direction that this point on the coupler is going to take at this instant in time as the linkage is moving. Right? Very useful. Okay. 5-bar linkages. Is there such a thing? What's a 5-bar linkage? Look at this pair of generically sometimes called vice grip, although that's a trademark. So these locking pliers. And these actually do happen to be real vice grips. How many links do we have in here? 1, 2, 3, 4. Why do we call this a 5-bar linkage? Is it? It's actually a 4-bar linkage, but something else is happening in here. What is happening? See this yellow line here? Watch what happens. As it goes and it goes up, and there's that little snap. What is it doing? Well, it turns out that there's an instability that happens when two of the links align, and you get immense force at the end. Bloomp. And then this little link here, you push on it, and it kicks it out of the instability. So it's really a 4-bar linkage with that extra link added in to help it get a secondary motion. What about bolt cutters? Are they a 5-bar linkage, or a 6-bar, or a 4-bar? And what do you do with bolt cutters, similar that with vice grips, or the knuckle linkage we talked about earlier, to give us huge increases in forces? Let's count up and find out what we got. Here's a link. That's one link. Here is another link. Here is the other half of the system, another link. We got pivots here and here. And now, got a link here, one handle. And then on the other handle is another link. Notice that the handles have these multiple connection points. Whoop, wrong color. So now let's count them. What do we got? 1, 2, 3, 4, 5. I've got n equals 5. 5 links. What kind of joints do I have? Whoop. Let me use a different color so I can see better. I've got 1, 2, simple pivots, 3, 4, 5. I have F equals 5 pivots. What does Grubler's tell us? 3 times 5 minus 1 minus 2 times 5. What's that? 4 times 3 is 12 minus 10 equals 2 degrees of freedom. What are the degrees of freedom here? I know when I push, crunch, these joints come together. What else could be happening? Are there 2 degrees of freedom? Look here with the system wide open. What is happening when I close? Is it okay to have 2 degrees of freedom? Is there some situation where I want to have less degrees of freedom? What is happening? Well, ask yourself a question. What does manufacturing require and like in terms of symmetry versus what do I actually need in terms of the functional requirements of here? Could this link here actually be, this is all one, so it's really a 4-bar linkage, and that's actually not a pivot. And that was the case, I'd subtract one from each, and I'd have 4 links and 4 pivots, which I know from a 4-bar linkage is 4 degrees of freedom. Could it be that bolt cutters are put together, these big, mighty bolt cutters, and that's just a way of manufacturing them? And this extra degree of freedom I'm getting is a little parasitic motion that doesn't really matter. And indeed, when you look at other bolt cutters, I have 1, 2, 3, 4 links, 1, 2, 3, 4 pivots, a 4-bar linkage on a small set of bolt cutters. Whereas on a giant set of bolt cutters, I have this design. Why is that? Okay? So you investigate and you look up and you think about how often do you find true 5-bar linkages, or are they really kind of a 4-bar linkage that's got an extra link thrown in for manufacturing? Okay? But definitely worth looking into. Okay, we'll come back with some really excitement, high levelness for 6 bars. Okay, so now let's look at the analysis of, quote, 5-bar linkages. It's basically the same thing as 4-bar linkages. Here is the 4-bar linkage from the vice grip example. And now look here of this line diagram of the bolt cutters. And I want you to start in your own design notebook with just this picture of the bolt cutters. How would you analyze this thing? As this thing moves and crunches down, what exactly is happening here? And forget the fact that we said that there's a redundant link going on. By symmetry, you can do this, and now we can put this as part of our ground link. Right? So you should be one step ahead of me as you're sketching in your design notebook. This here point on the ground can slide, and it can also rotate. That should trigger something in you about the earlier on the definition of joints, a 2-degree of freedom joint that can slide and rotate. And then here is this head. And there's a second joint here from the handle. I'm going to use a different color for the handle here so it's not so confusing. The handle comes here. And there is, this is now a joint that slides and rotates, and this is a pivot. Okay? So what is happening here is this handle moves down, this point goes up, this point here slides in. But this distance from here to here stays the same. So think about it a minute and draw in your notebook what's actually happening. Okay? And I'm guessing you drew something like this, that here is, this is to ground, this point here can move here, so at an instant in time it looks like a pivot. This point here, this dimension here is the same, so as I push down on the handle, this length is the same, this length is the same. Play the movie in your mind. This is going to go up, and these links, which are not collinear, will straighten out and actually become collinear. Right? The way I've drawn the purple here This is the jaws. And here's the cutting force. How would you solve these triangles, these angles, and come up with the motion here at the back at the handle times the force? How does that correlate to the cutting force and the motion of the tip? I want you to work through and try to solve that geometry problem. And there's a spreadsheet, of course, that goes with this, linkage 5-bar. See if you get the same answer. It's a really good problem to work with 4-bar, 5-bar, these 6-bar linkages, solving these networks of triangles. Go back and look up the law of cosines, the law of sines for solving triangles. For example, if I know this angle, this side, and this side I want to find, how do I find that? What's the law of cosines? How do I find that? This is one of the most powerful trigonometric relationships we'll use for solving these kind of triangles. Okay? So that's a very, very important skill to get up on, good mental push-ups, and it allows you to start writing your own spreadsheets to analyze linkages, and then also similarly to do the synthesis of linkage design. Very, very important. Okay? We're going to come back now with even more fun with 6-bar linkages.